And we are back again, and we have a task that's similar to one of the ones that we had before. We're being asked to find all the rational zeros of a polynomial and to factor it into linear factors. What you may notice, however, is that we aren't actually given a starting point. So with one of the others, we were given one of the zeros, and we had the opportunity rather to divide so that we are using that zero so that we would have a smaller degree polynomial to work with. This time, again, we don't have that starting point, so we need to come up with it on our own. And the way that we do that is using the rational root theorem. Now, what does this rational root or rational zero theorem say? It says that if I have a polynomial, f of x, and there's a rational root of it, a rational number is just a fraction, something of the form p over q, then I know that this top number has to be a factor of the constant term. In this case, that constant term is -8. So what are the factors of -8? Well, positive and -1 are factors of -8. Positive and -2 are factors of -8. So are positive and -4 and positive and -8. Okay, so if I have a rational zero, then the top number or the numerator of that zero has to be a factor of -8. The denominator or the bottom number has to be a factor of the leading coefficient, which in this case is a 1. So I have a list of possible values for the numerator and a list of possible values for the denominator. How do I take that and turn it into a list of potential zeros? Well, I just take all the numbers in the numerator and divide them by all the numbers in the denominator, which in this case is not super hard because 1 over 1 is 1, 2 over 1 is 2, 4 over 1 is 4, and 8 over 1 is 8. So I have 8 potential zeros. Not that any of these are actually zeros, right? It could be the case that I don't have any rational zeros, and so all these numbers could fail to be zeros. But if I do have a rational zero, it has to be one of these. So let's go ahead and get started testing them. I'll start with the -1. I want to see whether or not this -1 is actually a zero. So I'll set up synthetic division. And on the outside, I'm going to have a -1. That's the number I'm testing. And then underneath, I'm going to have a representation of this polynomial. So I'm going to take the coefficients 1, 5, 2, and -8, right? And again, I know that I'm okay here because I have one term of each degree. I have a degree 3, 2, 1, and a degree 0 term. All right, so let's drop the first coefficient, and then we'll multiply and add and multiply and add and multiply and add. And look at that, we have a remainder of -6. Since the remainder is -6, I know that this number that I divided by, -1, cannot possibly be a zero. Not that we did anything wrong, it's just that we performed the test, and the test told us that this number here is not a zero. So we move on. Now let's take another number in the list, like a 1, and test it to see whether or not it's a zero. And if you want to try this on your own, you can take a second to pause the video here. Nonetheless, we'll set up our synthetic division by placing the coefficients underneath. So 1, 5, 2, and -8. And then we'll drop the first coefficient and multiply and add and multiply and add and multiply and add. So we go from having one that's not a zero to finding out that it's opposite. +1 is in fact a zero, and we need to keep track of that. So we found one of the zeros, and one of the zeros is a +1. So how do I find others? Well, I'm going to take my quotient here, which is, remember, since this is x cubed, my quotient is an x squared, which will make this x to the first, and that's my constant term. So my quotient is x squared plus 6x plus 8. All right, so I found a zero of the original polynomial. Now my goal is to find a zero of the depressed polynomial, right? This result here. I could do that a few ways, okay? I could go back to my list, and start testing zeros again, all right? If you have a really long list, however, that's going to be kind of tedious. Another thing that we could do is, well, because we have a quadratic, we can find the zeros of this using the quadratic formula, right? Because remember, a zero is just a number for x that makes the expression equal to zero. So then we can solve this equation here using the quadratic formula. And what does the quadratic formula say? Well, it says that x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. And in this case, a, b, and c, they're just 1, 6, and 8 respectively. So negative b is negative 6 plus or minus the square root of 6 squared minus 4 times a times c, right, all over 2a. So we can simplify this further. Negative 6 plus or minus the square root. Well, 6 squared is 36, and 4 times 1 times 8 is 32. And 32 minus, or rather 36 minus 32 is a 4. You can just type that all into your calculator to come up with a 4 all over 2. So then this is negative 6 plus or minus 2 over 2. Okay, and remember, this literally means negative 6 plus 2, which is a negative 4 over 2, and that turns out to be negative 2. And negative 6 minus 2, which is negative 8 over 2, and that turns out to be a negative 4. All right. Okay, so there we have it. We started off with 1, 0, and we found it. And the result of the division was a quadratic. And because it was a quadratic, we had the option of using the quadratic formula. Now, right here, that is right here at this point, I said you have the option of using the quadratic formula. Okay, one of the options that we did discuss was continuing to find numbers from the list and checking them to see whether or not they're zeros. The other option, if it's short and easy for you, is to factor, right? So you could also solve this equation here by factoring. Okay, but it just so happens that the quadratic formula works every single time, so we may as well memorize it and learn how to use it well. Okay, nonetheless, I have 1, 2, 3 zeros. The zeros are 1, negative 2, and a negative 4. Okay, so we've done it. We have found all the rational zeros, and so we answer the question in part A. The rational zeros are 1, negative 2, and negative 4. And I actually know that I'm done, right? The reason I know that there are no more rational zeros is because there's a theorem, and it's in your workbook. It's called the number of zeros theorem. It says that if I have a polynomial of degree n, then I have at most n distinct zeros. Now, what does that mean in this case? I have a polynomial of degree 3. That means I have at most 3 distinct zeros. And look at my zeros. I have 1, 2, 3 of them. So I must be done. I can't have any more than that. So I know that this is an exhaustive list of zeros. Okay, so that's part A. How do I then answer part B? Well, once you have part A, part B isn't super hard. Okay, the factor theorem says that if 1 is a 0, then x minus 1 is a factor. Likewise, if negative 2 is a 0, then x plus 2 is a factor. And if negative 4 is a 0, then x plus 4 is a factor. You see how we just kind of changed the sign? So then I have factors. These 3 binomials here are factors of f of x. And I'm done. The only thing is I need to make sure that the first term that I get when I multiply these 3 factors matches the first term in my original polynomial. So when I multiply these 3 first terms, I'll get the first term. So x times x is x squared. X squared times x is x cubed. Okay, And notice that's exactly what we wanted. So then we're done. If my original polynomial had contained an 8x cubed, then I need to stick an 8 in front and I'd be done. Okay, but that's not the case here. And so we have our 3 zeros and we factored it into 3 linear factors. All right.